So, just as a heads up, we will, if we are back in person on Friday, have our Chapter 19 quiz. If we're not back in person, then I'll just postpone that until we are. But we will have to kind of keep going with the lectures just to keep up with lab. I really don't want to, because for one, we miss out on a lot of the demos. I will kind of do some when we get back in person, just a little delayed from lecture, but for two, it's not as good if we do it this way, but it is what it is for right now. So anyway, we are going to pick up on talking about capacitors. Last time we just sort of did a deep dive into them. The idea of them, their purpose is to hold charge so that it can be released later. We'll look at that near the end of the chapter as a storage of potential energy that can be released, but it is through this charge that's being pushed onto one plate and then off of another that builds up positive charge on one plate and negative on the other, and the separation of charge there is what leads to this development of potential energy. We said that the ability to store charge depends on a few things, but they are all things about the plates themselves, not how much charge or what voltage you're putting across the plates. So the ability to store charge, it relates charge and voltage, but it doesn't depend on them. It depends on how big the plates are, how close together they are, and whether you've got a dielectric in between them. A dielectric is just an insulator, but it's an insulator that can polarize pretty easily when you set it between the two plates. And what that does for us is weakens the overall electric field in between the plates, making it easier for more charge to move onto them. And that's really what is going to increase your capacitance in any case, is anything that's going to make it easier for more charge to get on the plates means you're increasing your capacitance, your ability to store charge. Another way I like to look at it that we didn't kind of draw here, I'll just mention it, is if we're thinking about this as electrons are trying to get onto this plate, that's really the thing that needs to happen to accumulate more charge. Well, if you have a dielectric in there, because of this polarization, look at these sort of adjacent charges. In that region, it's sort of like they neutralize each other out. And so as far as the electron that's trying to get onto the plates is concerned, it sees less charge than there was before. And so it's like, oh, there's plenty of room now. That's another way of seeing that adding a dielectric increases the capacitance, increases the ability for the plates to hold more charge. So, we did derive that relationship for capacitance, that it says it really does depend on all those things. It's just smashing together a bunch of equations, but the real important bit is what each thing is saying. It's saying the bigger the plates are, the more charge you can store, because the charge can spread out, meaning less repulsion of additional charge. Right, we talked about how the electrons are kind of kicking the ladder down behind them, making it harder for any additional electrons to get on the plate. If they're more spread out, they don't have as much of an ability to do that. Why does decreasing the distance between the plates help get more charge onto them? Well, remember what's on the other plate. Bunch of positive charge. For any electrons trying to get onto the lower plate, if there's a lot of positive charge nearby, it's helping the negative charge get on there. So while the other electrons are trying to push the additional electron away, the positive charge on the other plate is helping it. And the closer the plates are, the more it can help out. And then the dielectric, we said it weakens the field between the plates, making it easier for additional charge to get on, or the way I just talked about it, it is as if there's less charge on the plates. so more can flow on. Okay, and this is where I'm going to pivot to Eugene again, that video I had up, because I think seeing all of this really helps it sink in.
Now let us consider a new scenario where there is another metal plate.
Maybe 1.5 was too much. One sec. Let's try 1.3.
Close to the one shown. As electrons accumulate in the first metal plate, they will repel the electrons in the second metal plate. The positively charged particles left behind in the second plate will exert an attractive force on the negatively charged particles in the first metal plate. This makes it possible for the first plate to have more negative particles than positive particles. As we add electrons to the first metal plate, an equal number of electrons leave the second metal plate.
So this is just charging up
After
the
a certain
capacitor.
number of extra electrons accumulate on the first plate, they will repel any new electrons trying to enter.
Kicking
The
down
first
ladder
metal
behind
plate
them.
has developed a net negative charge, and the second metal plate has developed an equal and opposite net positive charge. We can cause this equal and opposite charge on each plate to be larger by applying a larger external force.
Attaching a larger battery.
If we remove the external force we are applying, the extra electrons in the first metal plate will continue to repel one another.
And that's just the discharging of the capacitor. So, the three things we looked at, the size of the plates, the spacing, and the dielectric, I'm going to jump around to, because you can see this video is 10 minutes long. I don't think it needs to be. So let's jump first to about here. And this will show what increasing the size of the plates does for you, the larger A.
This increased area allows us to push more extra electrons into the first metal plate and remove more electrons from the second metal plate without applying a larger external force.
Because the charge can spread out more. Alright, and then we'll look at the spacing, putting the plates closer together.
This is by moving the two metal plates closer together. Because the two plates are now closer together, they exert greater forces on each other's electrons. This attracts more electrons to the negative plate and repels more electrons from the positive plate, allowing the two plates to develop larger net charges for the same amount of applied voltage.
And in this case, when they say force, they really kind of mean voltage. I think force is a little bit of a misleading term. They're just saying if you connect a bigger battery, you're going to get more quote-unquote force. It's really a higher voltage, larger hill for charge to flow down. But anyway, that's putting the plates closer together. And last is the dielectric. And that's going to look a little bit weird compared to how we've done it. They're just showing the what we'd call polar molecules in the dielectric. Water is a polar molecule. It's something that orients to an external electric field, and that's what we were talking about when we looked at the sort of shifting of the electron clouds to cause one side to be negative and one positive.
Suppose that we add a special material in between the two plates. This material does not allow any particles to flow through it, but it contains molecules that change their orientation based on the charges of the two plates. These molecules exert forces that attract more electrons to the negative plate and that repel more electrons from the positive plate. The presence of this material has the exact same effect as does increasing the areas of the two metal plates.
All right. So that's Eugene's version, but I like it because it's real visual. Let's do some math with it. Especially sort of older keyboards, the ones that aren't the mechanical switches, the fancy ones, they would use capacitive plates as one way to sense that you have pressed the key. And so essentially what you do when you press the key down is you've got this uh, dielectric that's a little bit squishy, and so you would compress it if you press down the key. But that's going to change this spacing between the two plates, and that will change the capacitance. As that spacing goes down, what's going to happen to the capacitance of the plates?
Increase.
Increase. And that means if you're applying a fixed voltage across the plates, it's going to allow more charge to flow on, meaning a current will flow when you press down that key. And that's your way of sensing that that particular key has been pressed. So we're going to see how much the capacitance changes when we press that key. It's not a lot, but it can be sensed by the whatever circuit they've got connected to it to sense that current flow. So in this case, we've got this as our plate area. So that would be A. The capacitor is filled with a material of dielectric constant 3.5. Again, that means that when we put that material in between the plates, it weakens the electric field between them by a factor of 3.5. What change in capacitance? So change in capacitance, I would label change in C, delta C, is detected if the plate separation decreases from this to this. So that would be D is your plate spacing. So let's call this one D initial and then D final. All right, so change in capacitance. How do I calculate the change?
The final minus initial.
Yep. All right, so this is how we would find capacitance. But the only thing that changes between the two cases is the plate spacing D. And so if I want to save myself some calculator work, I could plug all this in right now, but since kappa, epsilon 0, and A are the same between the two, I'll factor them out. And then it's just plug and chug. So kappa is 3.5. It doesn't have units because it's a ratio of two electric field strengths. And there is epsilon 0, the permittivity of vacuum or air, roughly. Plate area. I didn't leave myself much space as usual, so let's scooch this a little bit. And then it's 1 over the final spacing. And 1 over the initial spacing. I get 19 times 10 to the negative 12 farads, or 19 picofarads. You don't see pico very often until you get into electricity, especially capacitance, charge, that kind of thing. So this is a really small change in capacitance because the spacing between the plates doesn't change a whole lot, but it's still enough to sense that that key has been pressed while others have not. All right, so that's the kind of calculation you can expect to have to do with capacitors. It's not too crazy. I want to look at a application of that. So an application of this is remote dielectric sensing. So if you see dielectric in some technology, because there are several that use it, there's something called, I think, tissue dielectric sensing as well. It is referring to that something's being used as a capacitor. In this case, it's this unit right here, and it looks like headphones because it's shaped like headphones. Okay, on We'll say a very boxy human body, because that's the best I'm going to be able to do. It sort of goes over your shoulder like this, and then the other side of the headphones goes on the back. Okay, and this is like a head strap so that it can sort of go around your collarbone and hold on to it. But that's really the idea of the thing. I may have it flipped around, but it really is like putting headphones on your shoulder. The purpose of it is it generates an electromagnetic wave. So it's not a static electric field like we're used to seeing where charges aren't moving around. It is a wave, but the idea is still similar to what we've looked at. In our body, we have something that acts as a very good dielectric, a very polar molecule, and we've got a lot of it. What do you think?
Water.
Water. If we go back up to our table up here, we see that compared to without water, the electric field with water is 80 times smaller. So, the strength of an electric field in our body is strongly dependent on how much water is present. The more water you have, the more attenuated that electric field will be. And so, compared to some reference value, whatever you put in, you measure what you get out the other side. That's why you have on one side of this, there's a generator, and the other side, there's a sensor. Depending on how much water it has to pass through here in the middle, that's going to change how much the electromagnetic wave gets attenuated, and you can use that to sort of check how much water is present. If you're doing that with the lungs, you might see there's too much water. There's a lot of fluid in there, a lot of fluid buildup. And it can tell you roughly where the buildup is as well. And this is what other types of dielectric sensing do too. They're checking for water content. All right, so let's do a couple things with dielectrics. These are probably the hardest conceptual questions in the chapter. They're the ones that people get wrong a lot because there's a lot of moving parts. So we're going to use our analogy of the water tower to help explain or make this a little bit simpler. So we got an empty capacitor connected to a battery and charged up. It is then disconnected from the battery and we insert a dielectric. What happens to the voltage, meaning potential difference, between the plates? So let's kind of read that and see what we can glean from it. We've got a capacitor. We connect it to a battery. That'll charge it up. Up until the voltage between the plates, I'll use green for that, is the same as the battery voltage. I'm using this arrow to say this is the higher potential, this is the lower potential. So again, think of this as your plates are rising up. The positive side is raising, the negative side is lowering to make a hill and a valley of potential. And the battery is allowing that hill to be set up. So the question is, if we then disconnect the battery from the capacitor and then throw a dielectric in there, what happens? Well, I know that inserting a dielectric is going to do what to the capacitance?
Weaken the electric field.
It weakens the electric field, and what does that do to capacitance? Does it increase it or decrease it?
Increase it.
Yeah, it makes it easier for more charge to get onto the plates. But in this case, we've disconnected the capacitor from the battery. That's where the charge is being pumped from. So if we disconnect our pump, we can't get any more charge on the plates. That's fixed. So disconnecting from the battery means that our charge can't change. But then the final thing to keep in mind is the relationship between charge, capacitance, and voltage. That right there. So capacitance relates charge and voltage. The easiest way is to kind of just look at the equation and see what happens. It's not the most sort of intuitive or satisfying way, but it'll get you there. So if this can't change, so Q itself is a fixed number, but the capacitance went up, what must happen to the voltage?
Down.
Yeah, it's a balancing act. For this to be an equation, the left-hand side always has to equal the right. But if this number is fixed, call it 2, you double this number over here by a factor of 2, this thing must have gone down by a factor of 2 to accommodate or maintain that value of Q. So that's the math way. Now let's do the water tower analogy for this. So we said a dielectric is like adding a sponge. I'm going to say, because like they said in the video, that has the same effect as increasing the area of the plates. Inserting a dielectric is a lot like making your water tower bigger. So in real life, that would be pretty expensive to do, but let's pretend you've got a slider that just lets you change the size of your water tower, make it bigger. But if the charge is fixed, that's like keeping the amount of water the same in the tower, okay? Because charge is like mass. That's our analogy here. Keeping the amount of water fixed. So come back up to way up here. The mass of water in the tower is like the charge on the plates. The height of the water level, is like the voltage across the plates. So if I make my tower bigger, but I keep the amount of water in it the same, what's going to happen to the water level?
Decrease.
Yeah, it'll drop, it'll lower, right? You've got the same amount of water, you've got a certain number of gallons in there, but the tower itself got wider. That's going to lower the water level. It's going to drop because you don't have to take up as much height with it. It can spread out more horizontally. So our conclusion is the water level or voltage drops. Final way is to tell you what actually happens. The physics. So when we insert a dielectric, we weaken the electric field between the plates. We don't have any more charge flow on because there's nowhere for it to come from if the battery's disconnected. But this does at least mean we can store the charge that is there more efficiently. It doesn't take as much energy to store it the way it is. And so it's like the hill gets a little bit lower. There's less potential energy associated with it. So inserting the dielectric, weakens the electric field between the plates. Also, if you remember that the electric field is like the slope, this is like saying the slope of the hill goes down. It becomes shallower. That means the change in height between the two plates gets smaller. Lowering the voltage. So the charge is stored more efficiently. Could also think of it like a spring. It is like the spring's relaxing. You don't have as much tension in there of it wanting to like go back to unstretched. That's what capacitors are like. It's a spring that really wants to snap back into place, and it can happen pretty dramatically, which I would normally show you in person, but I'll do a video today and show you in person on Friday. All right, so alternate question. If we kept the battery connected while the dielectric was inserted, what happens to the charge? In this case, if the battery is still connected, charge can move. So we're not constrained by that. We're constrained instead by the voltage. Because if the battery stays connected, it's what's controlling the voltage across the plates. It's setting it. So voltage can't change. But inserting a dielectric still means capacitance increases. So again, the math way. Tell me what happens to the charge in this case.
It decreases.
All right, well, let's look through it. So this is the thing that can't change. It is fixed. This is like a left and right arrow, just to say it can't go up or down, it's just got to stay where it is. But the capacitance goes up. So for this equation to still be true, what must happen to the charge, Q?
Increase.
Increases. It has to go up as well. Okay, for instance, if C was 1 and V was 1, now we double C to 2, but V is still 1, you have an overall product of 2. That means Q must have increased from 1 to 2 as well, for the equation to still be an equation, an equality. There's not really any substance to that other than saying we know the equation works. So let's do it the other two ways as well. That's just the quickest way. All right, so in the water tower analogy, it is still like making the tower bigger. But this time it's not the amount of water that's necessarily fixed, it's the water level, the height of water. All right, so if you've got some water in your water tower, but the tower itself suddenly gets bigger, and you still find that you've got the same water level, what's the explanation for that?
The amount of water increased.
Yeah, more water was pumped in. That's the only way you can keep the same water level in a bigger tower. Okay, and finally, for this I'll sketch out our capacitor circuit again. So you've got your battery charging up the plates to a certain voltage. But then we add in a dielectric. In this case, more charge is free to flow if it wants to. The battery can push more, and it does because inserting the dielectric, remember, induces an electric field that opposes the original one, and that makes it easier for more charge to flow onto the plates. So it's like the dielectric is kind of saying these positive charges are balancing out some of the negative that's on the plate, which I don't know if you can see my cursor in this view, but this positive charge and this negative charge are sort of balancing each other out, meaning it's as if there's a little less charge on that plate, and so more can flow on.
Why the direction, the voltage is different?
So the physics of what happens. When you insert the dielectric, it actually does change the voltage for just a moment because inserting the dielectric weakens the electric field. Again, that's like the slope of the hill. So the height of the hill must have gone down a little bit. But that means the battery is able to push a little bit more charge on because it's winning again. It's got a slightly higher voltage than the capacitor does, and so it has a little bit of room to push more charge. But that's not going to last long until it pumps enough charge onto the plates that the voltage is back to the battery voltage. So more charge can flow in. And that's going to happen until the capacitor voltage returns to whatever the value for the battery is. So to maybe put some numbers to this to help a little bit, let's say it's a 1.5 volt battery. It is going to push charge onto the plates of the capacitor until the voltage or potential difference between them is also 1.5 volts. The positive end of the hill is 1.5 meters above the negative end in this sort of analogy. But when we insert a dielectric, we weaken that field, we lower the hill a little bit, say to 1 volt, 1 meter of height. That allows the battery to push more charge onto the plates until we're back at 1.5 volts, 1.5 meters, but doing it with more charge. So that's another way of saying you've got more capacity to store charge at the same voltage. The capacitance is bigger. So let's then talk about that in terms of energy. So in terms of potential energy, think of how we build potential energy for gravity. We lift something up off the ground. We take it to somewhere it doesn't want to be, and that's how we store up energy. If you want to store up lots of energy, just lift a lot of stuff up off the ground, which is what a water tower does. It stores gravitational potential energy by lifting water up to a height. And then you can use that energy, turn it into kinetic to allow the water to flow later when other pumping systems are down. So it's a passive way of storing gravitational potential energy in the water system. Capacitors, same sort of deal. In order to store up potential energy, you got to move charge to a place it doesn't want to be. We've talked about that as the negative terminal of the battery pushing some negative charge to, in this case, plate B, and that pushes some off of plate A. We can equivalently think of that as I'm going to yank some negative charge off of plate A. I'll just scoop some off of there and bring it all the way down to plate B and plop it on there. And I'll just think about how much work it took me to do that. For each electron that I put on there, it's going to take a little bit more work because there's already some there, making it harder to put more on the bottom plate. So that's the idea here. Let's think about for the very first electron, what I have to do. So when I close this switch, which is me saying, all right, I'm going to start pulling electrons off of plate A and putting them on plate B. It's really the battery that has to do that. It's the one doing the work, but it's easier to imagine it's me pulling them off the top plate and putting them on the bottom. What potential difference do I have to move that negative charge through at the very beginning? So what is the potential difference between the two plates, A and B, when I first start this process? Let's go back to this kind of sheet pan thing that I had in class. That'll make it easier to see. When there's no charge accumulated on either plate, what is the potential difference between the two sides of the plate?
0.
0. It's sitting flat on the floor or flat on the table. Okay? But now, let's say there's some negative charge on one end and positive charge on the other because I pulled some negative off the left end, put it on the right end. Then we've got a hill. If I take even more negative charge off the left end, making it more positive, and put it on the right end, making it more negative, my hill has gotten steeper. As I keep doing that, which I don't know what happened there with perspective, but anyway, as I keep doing that, loading up more and more positive on one end and more negative on the other, I'm raising up the sheet in this sort of height analogy. That's what I'm doing with the potential difference or voltage between the two plates in this picture on the right as well. So when I first pull an electron off of plate A, leaving it a little bit positive, and put that electron on plate B, what is the potential difference between the plates for that? There's no charge on them yet, right? I'm putting the very first charge on them. So what is the potential difference?
0.
0. That's what I'm looking for. So how much work do I have to do to move an electron from plate A to plate B? Well, remember, work is charge times change in potential. That's from like very beginning of the chapter. There is a negative in the beginning of the chapter. That's because that's the work done by the electric field of the charges. I'm interested in the work I have to do to counteract that, in the same sense as there's a difference between the work I have to do to pick something up and the work gravity's doing when I pick it up. Gravity's doing negative work, I'm doing positive work. I'm interested in the work I'm doing right now, so I'd throw out that negative that's at the beginning of the chapter. So anyway, that's a long-winded way of saying, take the charge of the electron, which is negative E, negative that 1.6, blah, 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 multiply it by the potential difference that I had to move that electron through, which is nothing. Takes practically no work to move that first electron. But now I've got positive charge on one plate and negative charge on the other. I've got a slight difference in potential, a little v. Okay? I have to move my next electron off of the top plate and onto the bottom one through that little v of potential difference. That's going to take a little bit more work. It's like moving it up, or in the case of negative charge, moving it down a slightly steeper hill. And I'm going to do that over and over as I pull the next electron off, leaving the top plate positive, and set it on the bottom plate. That's going to build up even more of a little potential difference. And then the next electron I move is going to have to move through that, a steeper hill. It gets harder and harder to put more and more electrons on these plates as I load them up. And I'll keep doing that. And that's going to build up the potential a little bit more. The next electron has to move through that. So it's just getting more and more difficult to put any additional electrons on. It's another way of saying they're kicking down the ladder behind them. All right, it's just this building up and up and up and so on and so forth until that very last electron that I pull off the top plate and put onto the bottom plate. At that point, I'm practically having to move through this whole voltage, the battery voltage. The hill is about as steep as it can get because I'm struggling to get any more charge on there. And so I have to move that last electron through essentially the potential difference provided by the battery, but it'll be negative in this case because I'm moving the electron from this higher potential to lower potential. I'm making it go downhill, which it doesn't want to do. That's how I'm storing up energy in the first place. You don't have to worry about that negative too much. If it's confusing, it's just to get the numbers right. This is all going to be easier if we pretend it's positive charge, which we will start doing very soon. So this process keeps going until, instead of this little v, I've built up whatever the battery voltage is. Let's call that V0 maybe. So the very last electron that I move between the plates, I have to move it through a potential difference of negative V. So, wide range of amounts of work I have to do. The average amount of work I have to do is midway between those two extremes, right? I have to do sometimes more work than the average, sometimes less, but on average, I'm doing somewhere in between. That's my way of skipping the calculus involved in this. So, the total amount of work I have to do to move all those electrons between the plates, whatever charge I had to move in total times the average height of the hill. And that's going to be half its final value. Okay. On average, the hill is about halfway between flat and as steep as it can get. So, that's the amount of work I have to do to move all that charge, but that means that's also the amount of potential energy I've stored up as a result of moving that charge. So, the potential energy stored in that capacitor is 1/2 the charge on the plates times the voltage of the battery you're connecting to charge the plates up. The last thing is there's a relationship between charge and voltage for a capacitor. Capacitance relates the two. I can use that to write this in two other ways. I could either sub out for charge, write it as C times V. So I would write it like this. That's just saying that charge is C times V. Or I could sub out for voltage and realize that, oh, well, the voltage is just charge over capacitance. If I put that in instead, I could write this totally in terms of charge. Q squared over 2C. Sorry, no. We could put a 0 to say it's the final amount of charge, but anyway, lots of subscripts either way. Okay, so let's apply that. Let's see how much energy you actually store in a certain capacitor. This is a real capacitor that we have, and I will show you what it looks like when we store this much charge on Friday. But let's say you charge one that has this value for its capacitance until it has this voltage across its terminals. First question, how much charge do you have on the plates? Remember, it's positive Q on one, negative on the other. And how much energy do you store as a result of that charging? This is very plug and chug. How can I find how much charge is on the plates?
You can multiply the capacitance and the voltage.
Yeah, that's it. So capacitance is 4,500 microfarads, so 10 to the negative 6. Voltage is 225 volts. That is a charge of little over 1 coulomb, which we said a long time ago is a huge amount of charge. Again, I'm going to do this on Friday. I'm going to store this amount of charge, and then we're going to suddenly discharge the capacitor and see what that looks like. It's kind of scary. And let's see how much energy that stores. So how could we find that? How could we find how much energy is stored in the capacitor? Just what could we possibly do to find that? I'm running out of Zoom here, y'all.
Use the equation that you're zooming into.
Yes. I could actually use any of the three, because now I know how much charge there is as well. But this is the one that's just relying on what I was given and not what I had to calculate myself. $225 volts. And we square that. We find that would store about 114 joules of energy. To give you a basis for that, I said defibrillators are basically capacitors. The two plates you put on someone's chest are the capacitor plates. Depending on the type of defibrillator, because there's two main types, they can store and then deliver anywhere from 115 to 360 joules of energy to the heart. So, that capacitor I will discharge on Friday or whenever we make it back to in person it's storing as much energy as a defibrillator. And we're going to release it very, very quickly by connecting a conductor across the terminals, meaning the charge is really going to be ready to flow. That's called shorting out the capacitor. Do not do that. If you ever see one, I don't know where you would, but if you do see one, don't short out the terminals unless you know what you're doing, because it can be pretty dangerous. What I want to show you is someone who had an even bigger capacitor shorting it out. So mine's going to look a little bit dinky in comparison to this one, but this is pretty cool. So their capacitor, you can see in the description, is 21.5 microfarads, and you can charge it up to 30 kilovolts, 30,000 volts. That stores 9,270 joules of potential energy. We compare that to what my capacitor I'll discharge at some point in the future is. We're looking at, what is that, about 90 times the energy of the one I'll discharge. This is the type I was talking about that we have in our basement for some reason, but they have a bank of them, multiple ones, so you can charge them to an even higher voltage. I'm sorry, you can store even more charge at that voltage. And they're going to short it through a watermelon. What I want you to realize or keep in mind is there's not electrically that much difference between a watermelon and a human head. Okay? So, if you touch one of these, also notice, by the way, you can't tell when they've charged it up.
No.
It doesn't look any different once they do.
Eikä se tipu? Ei.
And of course this is in Russia.
Pistetään se vähän noin. Se ei kuule kerkiä tajuamaan, mikä siihen iski mehukasta. No niin, hyvä.
So that's your capacitor bank. This is what happens if you touch them and they're charged up and you don't realize it. So the watermelon's gone. Your head is gone. You are red mist. Do not touch things if you don't know how charged up they are. That's kind of the takeaway here. All right. That's a good place to stop. We finished this. We didn't quite get to chapter 20, my bad. But we will start that on Friday. This also means if we are back in person on Friday, we'll have our quiz over chapter 19. So be ready for that. If we are still closed on Friday, we'll just postpone the quiz to whenever we get back. But otherwise, we just kind of continue with the schedule as usual. So this is the cutoff for the exam as well, because it's 18 and 19. So this is everything that could be relevant. Questions on anything?
I followed the table and the conceptual bit, and then I got lost when we needed to take the average, so it became like half of the voltage,
Sure.
like in the work.
Yeah, so another way to phrase this is, say I had to move all that charge at once. How much work would it take? It's going to take whatever the charge I'm moving is times the average voltage that I'm moving them through. In reality, I know that some of it I'm having to move through practically no voltage at all. Some of it I'm having to move through the battery voltage, and then really everywhere in between. So the average voltage is just going to be what splits the difference. It's the middle ground of voltage. And that is effectively, on average, what each electron is seeing, if we sort of evenly distribute how much each sees across all of them.
I'm kind of there, but
Okay.
I'm kind of not. It's like, maybe I'm thinking about it wrong. Like, it's a point in time.
Let me put some numbers to it. That may help.
Okay.
So let's say our battery is a 3-volt battery. The first electron that I'm pulling off of the top plate and putting on the bottom one, it's not having to move through that. It's moving through practically 0 volts because there's no charge accumulated. The last electron's having to move through practically all 3 volts up to whatever it contributes once it's on the bottom plate. If we look at any...
Yeah.
Sorry, go ahead.
That's good. Sorry, I didn't mean to cut you off. The numbers, that's good.
Okay, yeah.
That made sense.
Yeah, so on average, I'm having to move them through a 1.5 volt potential difference, and that's where the 1/2 comes from.
Okay, thanks.
Mm-hmm. All right. And then any other? There was another question, I think.
Oh yeah, it has nothing to do with physics, but I was just wondering what
Okay.
you were gonna do since it's a snow day.
Um,
Not to be weird, just curious.
well, Toji has been going crazy because he's, part husky, so he loves this. And so we'll probably get out with him for a little bit. He looks sort of like a demon when you go out there in the snow, though, because he's like pitch black fur and those really blue eyes. So it's kind of scary. And he lunges at you because of how excited he is. Um, so we'll just deal with that. And then y'all don't know this, but I actually have two dogs. So Mina, she's newer. She's tiny and she's a ball of rage. So she doesn't like it as much out there, but we'll try and get her out there some too.